Hi everybody, in this video we're going to look at 4 different problems and we're going to be solving these problems using steam tables. So I'm just going to dive into the first problem really quickly, which is basically given for ammonia. And first of all, what we're going to do is we're going to list down the information that is given to us. So you've got ammonia that is undergoing an isothermal process, which means that the temperature remains constant. The initial state, so state 1 has a temperature of 84 Fahrenheit, and you've got a specific volume at state 1 of 10 feet cube per pound. And this is so this is the data at your state 1. Okay. And at state 2, so ammonia undergoes an isothermal process from an initial state to saturated vapor. So this is your state 2. Okay. And obviously the temperature remains constant, so T2 is equal to T1. These are the conditions that are given to you. You need to find out the initial and final pressures, which means you need to find out P1 and P2, and you need to sketch it onto a TB or a PV diagram. So how are we going to look at this problem? We've got temperature given to us, we've got specific volume given to us. So obviously we're going to go to the tables, thermodynamic tables, and we're going to look at the table that is given for ammonia. And that table is going to be table A13. And because we're looking at this in these units, so it's going to be table A13E. And this is from Shapiro's book. I'll write it down in the caption of this video, which book it is. So we go to this table and we go across this temperature, right? So we've got 80 Fahrenheit, and across this we've got now specific volumes given to us for at the saturated liquid curve and the saturated vapor curve. So if I draw the PV diagram, let's say, let's draw that diagram. Let's say we've got this PV diagram here. I got some kind of curve over here. So on this diagram, there's going to be a constant temperature curve. Okay, let me represent it by this. And so what this value represents is Vg. Let's say this is at 80 degrees. Okay, this is at 80 degrees. So at 80 degrees, you will have a certain point at which you will have the saturated vapor state. Okay, at this point, you've got your ammonia completely in the form of a vapor, and this represents Vg. Over here, at this end, you've got ammonia in the form of a liquid, completely liquid. So you've got Vf over here from the table. Okay. But what is given to you is that the temperature is 80 Fahrenheit, but the specific volume is 10 feet cube per pound. What that means is, so Vg's value is 1.9524. Okay, this is 1.9524. But your ammonia has a specific volume of 10 feet cube per pound. So that means that this value is higher than this one. Okay, so what that means is that on this curve, and on which side does specific volume increase? It's increasing on this side, right? Because it's 0 at this point, so it's going to be increasing at this side. That means you got your ammonia somewhere to the right side of this dome. Okay, but because you're looking at a constant temperature process, that means it has to be on this line. Okay, somewhere on this line. Let's say it's somewhere here. Okay, and this is going to be the point where you've got V1. Okay, so that means that ammonia at state 1, we've already discussed this, and if you haven't taken a look, I'll leave the link here for you so you can go through it again. What this means is that ammonia is in the form of a superheated vapor right now. This is superheated vapor region on this side. So ammonia is in the form of a superheated vapor because the given specific volume is greater than Vg. Okay, so that means you've got to use a different table now, and that is table A15E, which is going to give you the properties for superheated ammonia. Okay, and what are you going to do now? You're going to basically keep going through the table across, let's say, now you've got different pressures given to you. And across these pressures, so for example, let me just remove these. So let's say you've got different pressures given to you now. For superheated ammonia, you go through this and you see and match the value for a specific volume now. Right now what you see is that at 6 pound force per inch square of pressure, specific volume is way too high. It's 41, and then it keeps going down to 54. So obviously the specific volume that is given to us is not available here. That means we move on to the next pressure set. And for 8 pound force per inch square, we go through this column again. And again, we see that it's not here. So 6, 8, 10, we keep going on and on until we find a column for pressure set, okay, across which we see that we've got, okay, from the specific volume runs down from around 9 until 11. So our specific volume is going to be somewhere between these two. So what do we do? Because our specific volume is 10 feet cubed per pound, so it's basically between these two values. Okay, but the pressure is the same for all of these values, so that means that the pressure at the initial state is going to be 30 pounds pound force per inch square. Okay, so just write down the units here. This is your pressure at the initial state. Okay, and now after that, what is given to you is that this is completely converted into a saturated vapor. And now we look at the PV diagram again, and what's being told to you is, I'm just going to draw the same thing again here. You've got your state 1 at this point, okay, and now you're being told that it goes on and becomes a saturated vapor now. Okay, the temperature is constant, remember. So we are traveling on this curve from this side, because this is your T1 is equal to T2, let's say. It's an isothermal process. So you're going to move on to the saturated vapor now. And the saturated vapor is going to be here, right? That means, so you had V1, which was equal to 10 feet cubed per pound. And now your V2 at this point is going to be equal to what? It's going to be equal to Vg at this temperature, right? So V2 is going to be equal to Vg at the temperature that is given to you, which is 80 Fahrenheit. Okay, and that is which value? I'm just going to take you back to that table, A13, and across 80 Fahrenheit, the value for Vg is 1.9524. just plug that in here, 1.9524. Okay, this is in feet cubed per pound. And the pressure is going to be now this pressure, because this is the saturated pressure. Okay, so the pressure over here is going to be this one. So basically, your final pressure, which is P2, is going to be equal to the saturated pressure at 80 Fahrenheit. Okay, and that is 153.13 pound-force per inch square. Okay, so this is how you work it out. You should make a PV diagram or a TV diagram first, so you can actually visualize what the process looks like, and then you can move on to the thermodynamic tables and consult them to see how you can find out whatever is being asked of you. So I'm going to leave this for you to do. You can sketch this process on a TV diagram now. The process itself is from 1 to 2, so this is your process, and this is the direction of the process. So we're going to move on to the next question now. And in this question, you've got ammonia, which is stored in a tank. So you've got, let's say, a tank, and you've got ammonia that is stored in this tank. And you've got volume, which is given to you. So the volume is given to you, which is 0.21 meter cube. You've got to find out the mass. So you need to find out what the mass is, and you need to find out the pressure as well within this tank. Okay. What else is given to you? You are assuming that the ammonia is a saturated liquid at a temperature of 20 degrees Celsius. So it's a saturated liquid. Remember that. That's an important condition, so we're going to write that down here as well, that it's in the form of a saturated liquid. So now what are we going to do? Again, we're going to first of all draw the TV or the PV diagram. So I'm going to go with, let's say, the TV diagram this time. Okay. And what I'm being told is that it's a saturated liquid. So that means that ammonia is where would it be on this curve? This is your saturated liquid curve. This is your saturated vapor curve. So it's going to be, ammonia is going to be somewhere on this line, which means, let's say, somewhere here. Okay. So what am I going to do now? I'm going to go straight to the tables for ammonia. I'm going to go to table A13 now, because this is in SI units. I'm going to go across the temperature that is given to me, which is 20 degrees. Across 20 degrees, I can, because I need to find out mass, so mass I can find out in terms of basically volume, okay, which is volume of ammonia, which is given to me, divided by specific volume. Okay, and specific volume is something that I can find out through this table. So what is going to be the specific volume of ammonia for the conditions that are given to us? Because at this point we've got Vf, so that means that the specific volume for ammonia is going to be 1.6383 into 10 to the power minus 3. So your specific volume is going to be equal to the saturated liquid specific volume at 20 degrees Celsius, okay, and that is equal to 1.6386 into 10 to the power minus 3 meter cube per kilogram. And because I've got this given to me now, which is here, so I can go ahead and plug this in here, which is going to be 0.21 divided by this value over here, and that way I'm going to find out the mass, and it's going to come out, let's say, around 128 kilogram. Okay, simple enough. And I need to find out the pressure as well. So at 20 degrees, the pressure is 8.5762. So the pressure is going to be equal to the saturated pressure at 20 degrees, which is equal to this value, 8.5762 bars, and I just have to multiply it by 100 to get it in the form of kilopascals, because that is what I'm being asked here. I need to find it in kilopascals. So 857.62 kilopascals. Okay. So this is what this question was about. It's very important for you to, first of all, I cannot stress this enough, you need to make a PV diagram or a TV diagram for your question. It's going to make your life so much easier because you can visualize it then, that where does your state lie? Whether it's on one of these curves, the saturated liquid curve or the saturated vapor curve, whether it's within the dome, whether it's outside to the left of the dome, which would be which would be a compressed liquid, or it's towards the right side of the dome, which would be a superheated vapor. So it's very important for you to know how to make a TV or a PV diagram. It's simple. I'm just going to go to the next question. At the end of this video, I'm going to review again what basically a TV or a PV diagram is and how you represent what on it. Okay, I'm just going to briefly review that at the end of the video. But I'm going to move on to the next question now. And again, this is a question for which you've got propane, you've got the pressure given to you, you've got the temperature given to you, and what you need to find is the specific volume, and you need to find out the specific enthalpy. Okay, so you need to find a specific volume and specific enthalpy for propane at pressure, which is given to you. So this is value for P, and you've got temperature, which is given to you. So what are you going to do? You're going to go to the thermodynamic tables. Okay, you're going to go to the thermodynamic tables, and you're going to look at the table, and you're going to go ahead and make that TV diagram. Okay, so you make this TV diagram, some arbitrary curve over here, arbitrary dome, and now what we know is that, let's say you've got a constant pressure line on this. Okay, the pressure remains constant within this curve. Okay, so what that means is, let me change the color. So what that means is that from this point until this one, okay, you've got pressure, which is going to be constant. You're going to have temperature, which is going to be constant. Okay, temperature increases on this side while pressure remains constant on this curve, and temperature decreases on this side while pressure remains constant because you've got isobars. These are isobars, so the temperature is constant throughout. Okay, so now what you do is you go to the table, which is, let's say, the pressure table, because you've got pressure given to you. It's 800 kilopascals, so you convert it into bars by dividing it by 100, and so pressure is going to be 8 bars. So this is the pressure. Okay. Across 8 bars, though, what you see is that the temperature, the saturated temperature, is 18.33 Celsius, but the temperature that is given to you is lower than that. What does that indicate? The temperature over here, this entire region, okay, is 18.33 Celsius. If the temperature that is given to us would have been higher than this one, so if the temperature that is given is higher than the saturated temperature, which is here, then you're in the superheated region, you're in this region. But because the temperature for our case, the given temperature, is less than the saturated temperature, that means we are in this region on this side of the dome. And basically, our point is, let's say, the pressure is still constant. We are still on the isobar, but the temperature has reduced now. Okay, so we are on this side. So that means we need to move on to the compressed liquid table. But in a lot of cases, we don't have compressed liquid tables. And we've already talked about this as well. Okay, first we see that propane is in a liquid state. Okay, we've identified that. So what we do is, I've already talked about this, that you can basically approximate the behavior on this side, and you don't need to use the compressed liquid tables. And to do that, you've got equation 3.11 in Shapiro's book, which will tell you that you can just find out the specific volume by looking at the VF value in the temperature table. Okay? So instead of looking at the pressure table, what you do is you go to the temperature table, and this is the temperature table because the first column is the temperature column. So you go to table A16, which is also for propane. Okay, this is the temperature table, and across this temperature now, you can just go and look at what the value of VF is, and you can approximate the behavior. This is an approximation. That specific volume for this case is going to be equal to the saturated liquid specific volume at the temperature that is given to you. Okay, so that is how you approximate it. So that is going to be equal to 1.89 into 10 to the power minus 3 meter cube per kilogram. Make sure you write the units and don't skip them. The other thing that we need to find is specific enthalpy, and for that, again in Shapiro's book, from equation 3.14, you go ahead, and this is something we've discussed in one of my previous videos as well, that you can approximate the specific volume by, again, looking at, sorry, not specific volume, specific enthalpy. You can approximate it by looking at the saturated liquid specific enthalpy in the temperature table at the temperature that is given to you. Okay. So this was your specific volume, and now you go to enthalpy and you look at the value of HF, which is 95.1 kilojoules per kilogram. Okay. And again, make sure you write the units here with it. So this is how you find out. This is how you find out values for whichever parameters that you've been asked for if they lie to the left side of the dome, if you want to look at compressed liquid region, okay, because you've got the compressed liquid here. You've got compressed liquid on this side, okay, but you don't need to use the compressed liquid table. That is what I'm trying to tell you. In a lot of cases, we don't have those tables available to us. So we just make this approximation, and this approximation works. Okay? Makes your life simpler. So let's move on to the next question. But if your concepts related to the TV and the PV diagram are not clear, then maybe skip until the end of the video. Look at what I'm explaining over there regarding these two diagrams, and then come back to the problems and work them out. Otherwise, it's going to be a bit harder for you to understand what's going on. But okay, let's just look at this question first. You've got a tank, and this tank has got water in it. You've got 2 kilograms of water. So let's say you've got this tank, you've got 2 kilograms of water in it. You've got the temperature, the initial temperature that is given to you. So this is T1. And you've got quality, which is given to you, which is going to be X1. Okay. Heat transfer is taking place until the tank contains only saturated vapor. So this is your state 2. Okay, at state 2 you've got a saturated vapor. Kinetic and potential energy effects are being neglected, and the water is being taken as a system. So in this tank, what you can say is that the water is a closed system. Okay, water is a closed system in here. And what else? You want to find out the amount of energy transferred by heat. Okay, so that means you need to find out the value for Q. And what we do is that we assume in this that the volume remains constant and that the work done is 0. Because what we're going to do is we're going to be looking at the energy balance equation, which is in the form of delta KE, which is kinetic energy, plus delta PE, which is change in potential energy, plus delta U, which is change in internal energy, and that is equal to Q minus W. Okay, Q is heat transfer, W is work done. If you don't know where this equation comes from, go to second chapter in Shapiro's book, review that. I think you can look at the problem 2.7 or something like that. Just go through it. You're going to look at the energy balance equation over here and how you arrive to it. You've got one of my videos, which is titled First Law of Thermodynamics and its Review. That is going to tell you as well how you get to it. This is equation 2.35 in the second chapter. So go and take a look at that. And example 2.2. Okay, example 2.2, you're going to see where this equation comes from. So you're neglecting the kinetic and the potential energies. You're assuming that work done is 0. This goes out of the window as well. So you've got delta U, which is equal to Q. Okay, or in terms of, if I was to write it in terms of specific internal energy, then this is going to be in terms of mass as well. So mass into delta U, and delta U, once I open it, it's going to be small u, U2 minus U1, and this is equal to Q. Okay, so you need to find out the value for U1 here first of all, and for that you go to table A2. And what do you do in table A2? You've got temperature given to you, so let's go and take a look at 80 Celsius. And at 80 Celsius, because you're trying to find out internal energy, so you're going to look at this column. You've got UF, which is given to you, UG, which is given to you, and you've got quality given as well. Okay, so that means that if you were to draw a TV diagram, okay, whenever quality is mentioned, that means you are within this dome. Okay, so let's say you've got some constant pressure line, an isobar over here, and what you're being told is that you've got a quality of 0.6. Once quality is mentioned, then that means you are within this region, within the dome, okay, here. And that means, let's pick a random spot. Let's say this is your state 1. Okay, this is your state 1. And how do you find out specific volume in state 1? You're going to find it out in terms of this equation, which is also given to you in chapter 3 of Shapiro's book. UF at 1 plus X1 into UG at 1 minus UF at 1. Okay, so this is your UF at 1, this is your UG at 1. You plug them in here and you'll find out the value for U1, which which is going to be equal to around, let's say, 1623 kilojoules per kilogram. Make sure you mention the units here. And what else do you need to do? You need to find out the specific volume at state 1 as well, because for state 2 you've only got this information given to you, that is a saturated vapor. You need one more some kind of information so you can go ahead and find out U2. Okay, so what you do is you, again, just like this equation, you find out specific volume at state 1 using the same kind of equation. Okay, so instead of U, it's going to be V. Everything else remains the same, and so your V1 is going to be around 2.04. Okay, that's going to be in meter cubes per kilogram. So now that you've got this, what you can do now is, because you need to find out U2, but you can't find out U2 right now because the only information that you have is that it's a saturated vapor, and the other information now that you have is that you assume that the volume is constant. That means V1 is equal to V2, so specific volume is constant as well. So because you know the value for V2, so now what you can do is that it's 2.04. So what you can do is that you go into, let's say, this table over here, and because you're saying it's a saturated vapor, so on the TV diagram, that means that the state 1 is going to move as a fixed volume towards becoming a saturated vapor. Okay, so this is going to be state 2. So now what you do is you go into this column, and all you're concerned with right now is this information that is given to you, V2. You go in this column, you find out 2 consecutive values that will be of a range such that this value lies between the 2 of them. So obviously it can't be these 2 because these are way too high. So you keep going down the table until you get to, let's say, this point. And now this is the range in which you got your value for V2. Okay, so basically what that means is that your V2 is at a temperature which is between 90 and 95 degrees Celsius. Okay, so the temperature at state 2 is going to be between these two. One way to find this out is going to be to go ahead and apply interpolation. And we've already discussed interpolation. You can go back and take a look at this video over here and see how you can interpolate it. Or if it's not mentioned in the question that you've got to use interpolation, then what you can do is, you got 2.04, you can take ratios then. 2.04, and if you look at it from, let's say, this side from 2.361, then the difference is going to be 2.361 minus 2.04. It's going to be something like 0.31. And if you subtract 2.04 minus 1.982, it's 0.06. So 1/3 towards this side, 2/3 towards this side. So that's how you apply the weightage now. That if it was like half and half, so 1/2 and 1/2, 50%, then it would have been 92.5, right? The middle value. But right now, you've got 1/3 on this side and 2/3 on this side. So that means you divide, because this is a difference of 5 Celsius, so you divide 5 Celsius by 3. That's like 0.16 or something. Sorry, it's 1.66. And you multiply it by 2 on this side, so it's 3.3. Okay, and that means you add 3.3 to 90, so 93.3, or let's say you can say 93.5. So the temperature at 2, you can approximate it as 93.3, let's say, or 93.5 degrees Celsius. Okay, do you get this? That if it was, let's say, if this value was such that it was right in the middle of these two values, okay, then that means it's 50-50 ratio, right? So your temperature would have been 92.5. But because this value is leaning more towards this value, it's closer to this value, and closer by what amount? By 2/3 of the amount. So then the temperature is going to be closer to this value by 2/3 of the amount as well. That's why you add it to 90, or you subtract 1/3 from 95. Okay, and that's how you get the temperature at 2. Once you got the temperature at 2, what you can do now is, again, you need to find out U2. And how are you going to find U2? U2 is going to be equal to UG, because it's a saturated vapor. Okay, so it's going to be equal to UG at what temperature? At 93.3 Celsius. And again, to find this out now, you would have to interpolate. You would have to go into this column, okay, and you look at these two values. You don't have 93.3 in here, so you look at these two values and you use interpolation and you find out a value that is in the middle of these two. So let's say you apply interpolation, go and do that yourself, and let's say you get the answer as 2498 kilojoules per kilogram. Okay, that's the unit over here. So yeah, you obviously have to do interpolation at least once, but you saved your time by not doing the interpolation here if it's not being asked of you. But for this step, you obviously got to do the interpolation now. And now because you have the value for U2, you've got the value for U1, and mass is given to you as 2 kilograms. So you can go ahead and find out the value for Q, which is the amount of heat transfer, or amount of energy transferred by heat, and that is going to be equal to, for these set of values, it's going to be around 1750 kilojoules. Okay, so that is the value for Q now. Yeah, okay, so just to review, for any question, what you should do is, you should go ahead and basically make the TV diagram first of all, because that's going to save you a lot of headache, and you can basically go ahead and make your life easier that way. I'm just going to show you what the TV diagram is now, as I had promised, and basically you've got this some arbitrary curve over here. It says specific volume on x-axis, temperature on y-axis, and what's happening is that you've got constant pressure lines on this TV diagram. So for example, the pressure remains constant here. The pressure would, let's say, I'm just making isobars here, so let's say it's 10 megapascals over here. So it's going to be 10 megapascals throughout from this point until this point. And then once you cross this dome, then what you're going to see is that this curve kind of looks like this. And you're going to have, let's say, this is your critical point over here, and the curve on the critical point is going to be like this. Okay? So this is for water, let's say, it's going to be 22 something megapascals over here. And this is the curve for, let's say, 30 megapascals over here. And let's say this is some curve that is at 1 bars over here. Okay, 1 bar. So what I wanted to explain was that under the dome, you've got this region as a liquid vapor region. Okay, you got this region to the left side of the dome as the liquid region, and you got this region to the right side of the dome as the vapor region. This is also called on this side as the superheated vapor region. This is also called compressed liquid region. Okay. If you're towards this side of the curve, you should be using compressed liquid tables. If you're within the liquid vapor region, you should be using properties of saturated water, properties of saturated propane, ammonia, and stuff. So this is the table. This is the kind of table you should be using, the liquid vapor table. Okay, the name should indicate that clearly. And then once you're on this side of the region, you should be using the superheated vapor table. Okay. Also, some tips and tricks. If quality is involved, then that means that state is definitely between these two, because quality is between 0 to 1. So if you've got quality of 0.1 or quality of 0.9 or something, that means you're within this region. Okay. If you've got, let's say, given to you, let's say you've got a pressure given to you of 1 bar, so then that would be a different table, not this one. You're going to be looking at table A3. And that one, you're going to have pressure as the first column, temperature as the second column. So if in that table you've got pressure given to you as 1 bar, okay, and across that 1 bar, oh wow, okay. So let me just make that real quick. So yeah, you've got this curve, and in the pressure table you've got value of 1 bar given to you. In the temperature table, temperature column right next to it, you're going to have some temperature that is given to you over here, which is going to be the saturated temperature. Okay, and this is we're talking about table A3, I think, for water, which is the pressure table. Okay, so in that table now, the temperature over here that is given to you is the saturation temperature. And the saturation temperature is applicable from this point until this point. Okay. If, let's say, you've got a temperature given to you, okay, which is such that it's higher than this temperature. Okay. So the given temperature is higher than the saturated temperature, then that means that your temperature is, and the pressure is obviously constant, so the temperature is somewhere on this line, maybe here, let's say, and you should move from this table and you should go and use the superheated vapor table. If the temperature, the given temperature, is lower than the saturated temperature, then you go ahead and you look at this side of the dome, okay, and somewhere here, let's say, and then you're going to be using the compressed liquid table, or like one of the problems that we did in this video, where you use approximations, you use equations, and you don't need to use compressed liquid tables, because a lot of time compressed liquid tables are not available to you. Okay, so that is how you work with the TV diagram. This is the TV diagram. Okay, so if you understand the TV diagram, then the PV diagram is simple as well, and you can work with the PV diagram as well. Okay, so the PV diagram then is gonna have the same thing in a way. You've got, the only difference then is gonna be that the temperature isotherms. Okay, you've got PV, P on y-axis, V on x-axis, and then you've got these isotherms on here, okay, that are going to give you constant temperatures. And that is how you work with the PV diagram as well. Exactly the same, only difference is you've got, instead of isobars over there, you've got isotherms on here.